LED blink experiment. Let's start with the result. This LED is blinking on and off once per second. You can see here on the right side. At the first glance, this looks trivial. A light turns on, a light turns off. But what we are seeing is not a light experiment. It's an electrical experiment controlled by software. When the LED is on, the system applies about 3.3 volts on an output pin. So this is the output pin. In our case, is pin number 11. GPIO 70. You can see here. This voltage creates a potential difference across the circuit. The circuit is made up of source, resistor, LED. So we have source, and here is the ground of the source. Because there is a closed path, current flows. When the voltage is removed, current stops. The resistor is not optional. An LED is not a resistor. Once it starts conducting, it behaves almost like a wire. Without current limiting, the current would rise uncontrollably. Each output pin is driven internally by a small transistor. In our case is this one, the pin number 11. You can imagine here like a small transistor, and this transistor has a certain role. This transistor is designed for logic signaling, not power delivery. If too much current flows, the transistor can overheat and the output can be permanently damaged. The resistor protects both the LED and the transistor driving the pin. With proper sizing, current remains predictable and safe. If components are not sized properly, failures become dangerous. A damaged LED can behave like a short circuit. Without a resistor, this can effectively connect the output directly to ground. The resistor value was chosen deliberately. This LED drops about 2 volts, leaving about 1.3 volts across the resistor. This results in roughly 4 milliamps of current, visible, stable, and safe. Now let's look at the software. Setting the output to high applies voltage. Setting it to low removes that voltage. You can see here. We set it to high. Here we set it to low. The delays in the program control how long voltage remains applied. You see the delays here? We have two. The hardware continues operating even while the software is paused. This experiment is intentionally forgiving. Timing inaccuracies do not cause damage here. Later experiments will rely on this understanding. Software controls voltage. Voltage causes current. Components exist to make current predictable.